Hi there. Well, as promised, we're going to get into some examples that use the chain rule. Okay, in the previous two videos, we went through basically some of the understanding, the mechanics behind the chain rule, what makes the chain rule, why we have this notation, and why it works. So now let's actually go ahead and use it. Okay, so you'll notice I wrote both forms, both versions of the different notations up here. But I think when I'm actually doing these, I'm not thinking in terms of dy's and du's and dx, or even f primes and g primes. All I'm doing is I'm thinking, what is my outside function? What is my inside function? If I can keep those straight, then I can do any problem thrown at me. Well, what do I mean by an outside function? An outside function is really the last thing that you're doing in your function. So if you were to plug a value in for x here, you would square it, then you'd add x to it, but the very last thing you would do is you would cube it. Okay, so it looks like our cubing function is our outside function, and the inside function is what the cube is acting upon. So the inside function is this x squared plus x. Now, for all you mechanical people out there, it might help you to maybe make some substitutions here so that you can follow the pattern at least to get the hang of it the first couple of times. If we let u equal x squared plus x, then really what we have is y equals u cubed. And now all that's left to do is to follow this pattern right here. So what is dy du? Well, what is the derivative of y with respect to u? Let's just go ahead and write that down. dy du, all I need to do is use the power rule here, and it tells me that it is 3u squared. Okay, well, the second thing I need is du dx. What is the derivative of u with respect to x? And that's simple enough. I can use my power rule combined with my sum rules for derivatives, and I get 2x plus 1. Okay, so according to the chain rule then, dy dx, let me scroll up, I'm running out of room here. dy dx is equal to the product of those two rates that we just found. In other words, I just multiply these two together. Now, I want to make note of something. I really have a 3u squared here, I have an x here. I don't want u's in my final result. So what I'm going to do is I'm going to write in what u actually is. And u is really x squared plus x. So this right here is really this thing. Okay, that is 3u squared. Now we're going to multiply by du dx, which is 2x plus 1. Okay, and there you have it. You have your derivative. I suppose you could expand this. You could square this binomial and then distribute the 3 and maybe multiply it by this guy, but there's really no need to do that. You're done. You found the derivative using the chain rule. Okay, let's look at another example. And let's see, what do we have here? Let's go ahead and do, we'll use function notation this time. F of x equals, let's look at the cube root. The cube root of x squared minus 1, and we'll leave it at that right there. Okay, so the cube root of x squared minus 1. Well, again, if you want to, you can go ahead and set it up the way we did in the prior problem. Find an inside function, substitute u for it, and then go ahead and find dy du, du dx, so on and so forth. Or you could just think of outside function versus inside function. Okay, what is my inside function? Well, or more importantly, what's my outside function? My outside function, remember, is the last thing that you're doing. And the last thing we're doing here is we're taking the cube root of this inside function. So, before I take the derivative of this thing, I'm actually going to rewrite it. And I don't like cube roots, but I do like rational roots. Or I should say rational exponents. Okay, so the raising something to the 1/3 power is the same thing as cubing something. So really what I've done is I've turned this into a problem like the previous problem. Alright, so I'm going to first take the derivative of the outside function. Now the better you get at this, the less you will have to use the substitutions like we did up above. So if this is my inside function, what's the derivative? Just so that you can see it better. What would the derivative of u to the 1/3 be with respect to u? Well, it would be 1/3 u raised to the negative 2/3 power. But we know that u is really x squared minus 1. So I'm going to bypass the step that we did up above. And again, if you need to make that substitution like we did up above so that you can see it, there's nothing wrong with that. Okay, multiplied by what? Well, this is the derivative of my outside function. I need to multiply it now by the derivative of my inside function, which is x squared minus 1. Now I'm going to use some parentheses here just to make sure that I multiply by the entire function, just in case there's more than one object in it. Okay, so what is the derivative of my inside function x squared minus 1? Well, it's just 2x. And I guess I didn't need my parentheses after all, but that's okay. Okay, the last thing to do here would be to maybe simplify this a little bit. Typically, we want to maybe deal with the negative exponent. It's not that big of a deal, but you can do that if you'd like. Okay, let's go ahead and see if we can't simplify this. A negative exponent, if I bring it downstairs up in the numerator, I really have a 2x now, which is this guy. And then down below, I really have 3 times x squared minus 1 raised to the positive 2/3. X squared minus 1 raised to the positive 2/3. That's a 2, not a 1. I know that. There we go. Okay, so this is your derivative. Some of you may say, well, you can take the cube root of this and then square it. Fine, that's perfectly okay. Some of you may like this form better. One is not necessarily superior over the other. So we have found our derivative. Okay, let's look at this last example here. And what we have here looks like we have a quotient. So you might be thinking quotient rule, and you can certainly use quotient rule if you want. I don't usually like to use quotient rule if I can turn it into a product rule problem, or maybe something simpler. Okay, so this is -2. So really what I've done is I've taken this quotient, I've turned it into a product instead. Okay, so now we could actually use, if I asked you this, if I said what is the derivative of -7x to the -2? Okay, what's the derivative of this with respect to x? Hopefully you would say, well, you bring down the -2, multiply it by the -7 to get 14, and let's do this here, y equals that, so dy dx equals 14x to the -3. Okay, all I did was I brought this down, multiply it by the -7, decrease this power by 1. Okay, well, we're going to do the same thing here, because remember, power rule or chain rule says if you want to find the derivative of a composite function, that you first have to find the derivative of the outside function. And let me just make this clear. The inside function is going to be 2x minus 3. And so really what we're doing is we're doing this problem up here. But now we have this inside function that we need to take the derivative of, and it's just 2. So here's the derivative of my outside function, the derivative of my inside function. I can bring this 2, multiply it by my 14, and my final derivative is going to be 28 over 2x minus 3 cubed. Well, there you have it. You have 3 examples to get started using the chain rule. In the next video, we'll look to some more complicated examples. We'll see you there.